Host. Good morning. Welcome back to Intro to Speech Understanding. As I think I've described to you a few times, we've reached sort of the most mathematically intensive part of the course, and maybe the next two lectures are that most mathematically intensive part. You've learned everything you need to know about the basics of programming in Python, and you've learned about how to use NumPy in order to create matrix and vector arithmetic. I've taught you about the speech production mechanism, how we have a series of periodic closures of the vocal folds. And every time the vocal folds close, we get this negative pressure spike that excites the resonant frequencies of the vocal tract. And then I've told you about how all audio, including speech, can be viewed as being the addition of a whole bunch of sine waves added together. And if you want to find out what the frequencies and amplitudes of those sine waves are, you can do it using the Fourier transform. And that Fourier transform method turns out to be a more general method for both synthesizing and analyzing natural speech signals than the resonant frequency method that I described to you 2 lectures ago. So you know that speech is an impulse train, which excites a set of resonant frequencies in the vocal tract. But if you're given a new speech signal that you've never seen before and you want to try to understand the content of that new speech signal, how do you do that? How do you get the information in order to find what kind of vowel or what kind of consonant is in that new signal? And one answer, one of the best answers, is that you can use the Fourier transform. You can use this Fourier analysis to break down any signal into a whole lot of sine waves and cosines, and to find out which of those frequencies have the largest amplitude. And if you can find a couple of those frequencies that have larger, so all of those frequencies that have large amplitude will be multiples of the pitch frequency. If your pitch is at 100 hertz, my pitch right now is at probably around 100 or 120 hertz, meaning that my vocal folds are closing about 100 or 120 times per second. If your pitch frequency is at exactly 100 hertz, that means that the speech signal will only have energy at multiples of 100 hertz, at 100, 200, 300, 400, etc. Right? So if you do a Fourier transform, you should see energy only at those frequencies that are multiples of 100 hertz. But then the other thing that we saw 2 lectures ago is that you have resonant frequencies where there's more energy than in the neighboring frequencies. And at those resonant frequencies, say 500 and 1500 and 2000 hertz, at each of those resonant frequencies, you should have an even higher amplitude. So there's only significant amplitude at multiples of the pitch frequency, but those multiples that fall on top of a formant are going to be even higher in amplitude. I forgot, I'm going to go ahead and start transcription right now in order so that when I'll do it in English. And by starting a transcription in English, that way when I upload it to YouTube, that transcript will be available so that you can read through what I'm saying and go back and look at it if it's useful to you to do so. All right, so this week, what I want to talk about then is the Fourier analysis of synthetic speech. And we will analyze synthetic speech to find out the amplitudes and the frequencies of each harmonic of the pitch. And then next week, we'll do the same thing for real natural speech. We will analyze real natural speech to find out the amplitudes and the harmonics, the amplitudes and the phases of each harmonic of the pitch frequency. And we'll use that to resynthesize the speech signal entirely on the basis of those harmonic frequencies using the Fourier transform. So again, this week I'm going to use the FFT, but I'm going to use numpy.fft. I'm not going to try to do everything in terms of my own FFT matrix like we did last week. Instead, this week I'm just going to type np.fft.fft to find the spectrum every time. And so what I want to talk about, first of all, is the excitation, which you remember is that impulse train, because every time the glottis closes, you get this negative pressure spike. The air pressure above the glottis drops down suddenly. So I want to take that impulse train and do its Fourier transform in order to find out at what frequencies is there an amplitude in the signal. And then I'm going to take that synthetic ah vowel that has its resonant frequencies, its formants are about 700 and about 1100 hertz. And I want to do a Fourier transform analysis of that ah vowel in order to be able to see that higher amplitude at around 700 and at around 1100 hertz. And then I'll do a Fourier analysis of a whole bunch of different vowels, and then we'll take a look at the homework. So let me try to do those things. So first of all, let's try creating that impulse train. In lecture 7, we learned how to synthesize speech. In lecture 8, we learned how to use the Fourier analysis to find out which pure tones are part of a musical chord. So first, let me create this excitation. Let me start out with a sampling frequency of 8,000 samples per second. And I will have a pitch frequency of exactly 100 hertz, meaning that the vocal folds are closing 100 times per second. And I'll just make it 4,000 samples long. And I'll do an FFT that's 4,000 samples long. I'll use a pitch period in samples, which is the number of samples per second, Fs, divided by the number of pitch cycles per second, which is F0. And then I'll create an excitation signal, which is all zeros, except that once every T0 samples, I'll put a -1. And then if I plot that using matplotlib, the result looks something like this. Right? The result looks like a sequence of samples, and then once every 80 samples or so, there's a -1. If I play it using IPython, I get something that sounds like this. Right, so it's just a buzz. It's that buzz that if we added the formant frequencies, if we filtered that using the resonant frequencies, then we would get something that sounds like a vowel. But right now, it just sounds like a buzz. So we'll try taking the Fourier transform. Remember that the frequency of any particular component in the Fourier transform is the sampling frequency, samples per second, divided by n, which is the total number of samples in the Fourier transform, multiplied by k, which is the sample index of the particular frequency sample that we're looking at. So we have k over n is sort of a fraction. This particular sample is what fraction of the total samples, and then we multiply by that by fs to get the sampling frequency in hertz. And so I'll create the FFT of the excitation by just typing np.fft.fft. And that takes the input time domain signal and it generates as an output a complex valued vector where each sample of that vector, the kth sample of that vector, contains is a complex number whose magnitude and phase are the magnitude and phase of that original signal at the frequency f, which is fs times k over n. And so I can plot that as a figure. I can plot the absolute value of the FFT of the excitation as a function of f, the frequency in hertz. And that should show me the excitation spectrum with a pitch of 100 hertz. You can see that the frequency axis here goes from 0 to 8,000. And that's because in those capital N samples, we went from 0 up to the sampling rate, which is 8,000. So let's see, 8,000 hertz, probably there's about 80 spikes here, but it's really hard to see exactly what the frequencies are where it has non-zero amplitude. And so in the second plot, I've just zoomed in to the lowest 500 hertz. Sorry, to the lowest 500 samples. The lowest 500 out of those, let's see, how many did I have? I had a total of 4,000 samples. So the lowest 500 should be the lowest 250 hertz, I guess. 4,000 samples for 8,000 hertz means that 500 samples should be the lowest 1,000 hertz. I'm sorry. So if I plot that, I get again, here's the total spectrum, and then here's the spectrum zoomed into the lowest 1,000 hertz. And in that lowest 1,000 hertz, the lowest 500 samples, you can see that there's a large amplitude at 0 hertz, and again, a large amplitude at 100 hertz, and at 200, and at 300, and at 400, and at every multiple of 100 hertz. And in fact, here's a funny thing. All of those different harmonics have exactly the same amplitude. This is because of this particular special signal. In the time domain, this is just a sequence of impulses, one impulse every 10 milliseconds. And since all of these impulses in the time domain have the same amplitude and everything else is 0, when I take its Fourier transform, I discover that it has the same energy at 100, 200, 300, and 400 hertz. So this is kind of one way of saying this is that the Fourier transform of an impulse train is an impulse train. If it's an impulse train in the time domain with no variation, just simple, all of these have the same amplitude in the time domain, then in frequency, they also all have the same amplitude. This is unique. For most signals, that's not the case, right? If you take the Fourier transform of a regular speech signal, you don't get a regular speech signal. This is unique only to the impulse train. When you take the Fourier transform of an impulse train, you get an impulse train. And so I've written that here. The discrete Fourier transform of an impulse train with period t0 is an impulse train with period f0. The period here is f0, meaning that it repeats once every 100 hertz, 100, 200, 300, 400, and so on. So we can say that, in fact, it seems that the voice speech has a pure tone component at every multiple of f0. That is, f0 is 1 over t0. So we have, this has an amplitude of 50 at a frequency of 100 hertz. And so I can say, let me take the cosine at 100 hertz, and let me take that as a function of n. And let me take the cosine of 200 hertz. Let me set L equals to 2, and then I'll take 2 over 1/100, so 200 hertz. And at 200 hertz, I should get another cosine. And then up here at 300 hertz, I get another pure tone component. And so what this formula is doing is it's sort of, I'm saying, let me say that x of n is equal to, and let me say the x, capital X sub L, where capital X sub L is the Fourier transform component. At the frequency sample number L, which is F equals Fs times L over capital N hertz. So let me rewrite that. You can see that what I've written here is that x of n is equal to the sum over L of x sub L times the cosine 2 pi ln over t naught, where x sub L is the Fourier transform component at F equals Fs L over n hertz. And so we have L over t naught, L over t naught hertz. Because that's the harmonic number L. Okay, so we have the Lth harmonic. So 1, 2, 3, right? The Lth harmonic has a frequency of F equals L over T naught hertz, or L times F naught. So we can actually take these X sub Ls, these are all 50, we can just add them all together, add together a cosine at every single one of those frequencies, and we should get back again the original signal. Let me try that. Let me say for L in the range of 0 up to T naught, where T naught is the number of periods. I'll take my excitation E, which is just a sequence of zeros, and I'm going to add to that excitation the cosine of 2 pi times L, which is the harmonic number, times N, which is the vector of samples, right? Divided by T naught. So 1 over T naught is 100 hertz. And I'm going to show just the zeroth component and the first component and the second component. And I'm going to add each of them together to kind of give you a feeling of how that goes. So when I just have the cosine at 0 hertz, well, the cosine of 0 is always 1, right? So when I add in the cosine of 0, this is if I just take the inverse Fourier transform of this 0 hertz component, the cosine of 0 is always 1. Now the second component, the second plot, subplot L percent 8, right? The second component, I add that in. I've got the 0 hertz component, which is just a 1 everywhere. And I add into that a cosine that has a frequency of 100 hertz. Right? And so that cosine goes from +1 to -1. That cosine that goes from +1 to -1 is being added to a constant at 1. And so I get a total signal that goes from +2 to 0. This is the addition of the 0 hertz component and the 100 hertz component. Now I'm going to add in the 200 hertz component. You can see that it goes down and up and down and up again. So it has 2 complete cycles in 1/100th of a second. And what it's done is it's added together at the beginning of each period. It's even larger, right? I've got 2 plus 1. It's actually a height of 3 here because I'm adding together 3 cosines at the beginning. Nowhere else do they all add together. Here they're kind of canceling each other out. Here it's kind of canceling out this middle part, so it's risen a little bit. Here they're kind of canceling each other out. The only place they all add together is right at the end of each period. So at the end of each period, I've got 3 harmonics added together, and so the height is 3. Everywhere else, these cosines are all adding together out of phase. Some are positive and some are negative. And so when I add together, a positive cosine and a negative cosine, they kind of add together to get close to 0. And it gets more and more like that, the more of them that I add together. When I add in the 3rd harmonic, I get something where you can see the 3 complete cycles per period. But you can also see that now that I'm adding together 4 harmonics, I get an amplitude of 4 at each period. And in between that, it's closer and closer to 0. When I add together 5 harmonics, the constant plus 4 cosines, I get an amplitude of 5 at each period marker. And it gets even closer to 0 in between. When I add together 6 harmonics, the constant plus 5 cosines, I get an amplitude of 6 at each period mark, and it's even closer to 0 in between those, right? When I add together 7 harmonics, the amplitude is 7 at each boundary, and it's even closer to 0 in between. Until finally, when I add together all of these 80 harmonics, the constant plus 79 other cosines, I get something which is plus 80 at each period marker, and absolutely 0 in between. If we want to, we can then listen to that. Let me try listening to it. Let me take where's the IPython? Here's the IPython. Let me try displaying that. I don't want to copy the cell. I just want to copy this. Can I copy just that? Let me add that here so that I'll add an IPython display. Oh, let me just insert it below. Can I do that? There we go. IPython display, and what I want to display is this signal that I just created, which I called E. So let me try playing back the E signal. And now that E signal that I've constructed by adding together cosines, that should sound exactly like the buzz. It looks exactly like the buzz, so it should sound exactly like the buzz. And there it is, right? We've created back again that original buzz by just adding together all of those harmonics, each of them scaled by the Fourier series coefficient, which was the same Fourier series coefficient for all of them. In fact, this Fourier series coefficient should have been 50 rather than being just 1. And so I could make it 50 by just adding together 50 times the cosine, right? X sub L was actually 50, it wasn't really 1. So let me add together 50 times the cosine, then when I add together 80 of them, the total should be 50 times 80, or 8,000, 4,000, I guess. So when I go down to the bottom, the total is 50 times 80, which is 4,000. If I play it back again, it should sound the same, right? I've just increased the amplitude, and NumPy automatically normalizes the amplitude, so it sounds the same. NumPy automatically plays it back with a normalized amplitude so that the total amplitude being 4,000 instead of 50 doesn't really matter. So what we've got is actually that the impulse train, which is 1 impulse every t0 second samples, right? We've got delta is equal to, delta is a delta function. That's the function which is 1 when n equals 0 and 0 otherwise. And if I take a whole bunch of those and shift them by exactly 80 samples in time and add them all together, I get something like this, right? Here it is at time 0. Here it is shifted over to time 80 samples. Here it is shifted over to time 160 samples. And what I've shown is that I could recreate that impulse train in the time domain by actually adding together a whole bunch of cosines. This is actually the inverse Fourier transform. If we go to NumPy, we can find numpy.fft.ifft, and it will talk about the inverse Fourier transform, right? The inverse Fourier transform takes as input an input array, which might be complex, which is the Fourier transform of the signal. And what it generates as output, the output is, do we have examples here? Oh, here, right? I take the input, which is some signal n, and I compute its inverse, and I get some signal s, which is the inverse Fourier transform of that of the signal. So if I take what I've done here is I've taken this Fourier transform and I've inverted it using the IFFT, and I get something that looks like this. In fact, let me do exactly that. Let me change that and say new excitation is equal to the real part of the IFFT of the excitation spectrum. What was the excitation spectrum called? I called it excitation FFT. And let's just plot it. Let's stem plot it actually. And let's stem plot only say the first 500 samples of it. And we get that we've taken the IFFT and we get back again that same impulse train. Let me play it. Oh, not excitation FFT. I want new excitation, new excitation. Let's see if I've remembered all those things correctly. So now we can see that the excitation signal looks like, again, an impulse train with one impulse every 80 samples. And if we play it, it should sound the same. So we can get back that impulse train by taking the inverse Fourier transform of the excitation FFT. And that's essentially what I've done here. I changed the sign. I added plus 50 instead of minus 50. Let's make it minus 50. That should give us exactly the same signal. If we take minus 50 here, then lo and behold, we get -1 every 80 samples and zeros everywhere else. So we're getting back again exactly the same signal. This is -1. This one is -4,000. Why is that? Maybe I need to divide it by 4,000. All right, so I've got a scale. I'm off by a scalar somewhere. Let me divide it by 4,000. That should give me back my -1 everywhere. Yep, there we go. I've got -1 once every 80 samples. If I take the inverse Fourier transform of the excitation FFT, I get -1 every 80 samples. So what I've shown you is, in fact, I've sort of mechanically done the inverse Fourier transform. I didn't have to pay much attention to the phase. I just used -50 here because the phase doesn't matter for this very simple signal. For this very simple impulse train, all that I need to do is I need to take those cosines and add together all those cosines. And that's, in fact, the inverse Fourier transform of that spectrum. All right, all of that is sort of, so I've taken this impulse train, which we know is the excitation in speech. And I've shown you that the Fourier transform of an impulse train is an impulse train. And so we have, if we have one spike every pitch period in the time domain, then that means that we have one spike at every multiple of the pitch frequency in the frequency domain. And so we can construct the speech signal by just taking those spikes once every pitch period, once every pitch frequency, and inverse Fourier transform it. And we get back again, at least that buzz. All right, so what do I say here? We can see that the voiced excitation really is a sum of cosines at every integer multiple of f0. So we can take that impulse train in the time domain, that's equal to a sum of cosines. Each of those pure tones is called a harmonic of the pitch. So the 0 hertz component is called the 0th harmonic. The harmonic at 100 hertz is called the first harmonic. The harmonic at 200 hertz is called the second harmonic, and so on. So if I can plot all of those first harmonics. Let's see, what am I doing here? We have the first L harmonics, and we're going to create 80 harmonics. And I'll start out with a spacer which has 0. And then what I'm going to do is for each of those 80 harmonics, let me let me create like, let me add together. I'll create the first L harmonics, which will be all zeros to begin with, and then I'll add in ones. And then after I add in ones, I'll add in the second the first full harmonic, and then I'll add in the two harmonics and so on. And it becomes gradually more and more like a buzz, as you see. As I go through and add in more and more of the harmonics, this signal becomes more and more like a buzz until eventually it will sound exactly like a buzz. And I think what will happen if we listen to this is that I'll be able you'll be able to hear that first it just sounds like a pure tone. And then it sounds like two pure tones added together. And then three pure tones added together. And then gradually it will become more and more buzz-like as we listen to it. I don't know if you heard it, but you could hear each of those tones being added in one by one, because when the next tone, the next harmonic first appears, you hear it separately as if it's something new being added to the signal. So it went boom, 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 like going up at 100 hertz every time, right? One thing that was kind of interesting, if you noticed that as it was going up, is that once it gets past 4,000 hertz and starts moving toward 8,000 hertz, we start getting aliasing. Right here, I'm adding in the first 14 harmonics. When I get past 4,000 hertz and start adding in things that are going up to 8,000, let me show here's the entire spectrum, right? From 0 to 8,000 hertz. And it was adding these in one at a time, 0, 1, 2, 3, 4, etc. As it goes up toward 4,000, those tones that you hear being added in were actually going up in frequency. Boom, 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 boom. Once it gets past 4,000, it keeps going up in frequency, but it sounded like it was going down in frequency. I don't know if you noticed that. If you want to listen to it again, you can do that on your own notebook. I won't play it here. But past about the middle of that sequence, the extra tone that it was adding sounded like it was coming down in frequency. Boom, 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 right? And that was because of aliasing. That was because when you go from 4100, 4200, 4300, 4400, those are all being aliased back to 3900, 3800, 3700, 3600. So after about the midpoint of that sequence, it sounds like the extra tone that's being added in every time is dropping in frequency, when in fact it's increasing in frequency. And the sound, the only reason it sounds like it's dropping is because of aliasing. All right, fun with pure tones. Let's go on to talk about speech. So you remember that in order to synthesize speech, the way we did it is we took that impulse train and we passed it through a resonator. Here's that resonator again. So C is equal to the negative exponential of 2 pi times the bandwidth times Fs. And B is equal to 2 times e to the minus pi bandwidth over Fs times the cosine of 2 pi f over Fs, where F is the formant frequency and BW is the formant bandwidth. And then A is just 1 minus B minus C. And we add together each sample of Y of n is A times the input plus B times the previous output plus C times the second previous output, right? And when we add, this will just, if I run this code, it will just define the resonator function. And then when we give it those resonant frequencies, we can make an ah sound by giving it an F1 of 700 hertz and an F2 of about 1400. We can make an E sound by giving it an F1 of about 350 and an F2 of about 2400. We can make an oo sound by giving it an F1 of about 400 and an F2 of about 800. A, E, oo, A, O. We can make an A sound by giving F1 of 500 and F2 of about 2100. We can make an O sound by giving F1 of 500 and F2 of about 900, right? So we can make each of the 5 basic vowels by giving it different combinations of F1 and F2. So for example, in order to make an ah, I give it a resonator with a F1 of 700 and F2 of about 1300. Here it looks like 1400. Let me change that. And then an F3 of about 2500, F4 of about 3500, because those frequencies don't matter as much. We need to make sure that we have them, but exactly what frequencies they are is not so important. And so now we've changed that buzz into an ah. Almost sounds like my voice, just a little bit lower, I guess. All right, so now we know that we have formant frequencies from 700 up to 3500. If Fs is 8000, then Fs over 2 is 4000. So we can plot just that part of the spectrum, the non-aliased part, right? Let me take the speech FFT and let me just take that speech signal and take its Fourier transform. And then I'm going to create two subplots. In the first subplot, I'll plot the Fourier transform of the excitation. And in the second subplot, I'll plot the Fourier transform of the speech. Here's those sample times. Let me just create plot that with respect to f. So they plot f of up to 4000. F is equal to n. Let's see. Am I taking an FFT with a sample with a length of 8000 or 4000? I forget what length, how long f is. Let me just try f up to 4000 and see if that works. Let's see if that works. Nope, that didn't work. Let's see, will that work? Just make a sample array up to length of 4000. No, that didn't work either. Oh, np dot zeros with a length of np dot a range is what I want here, isn't it? Let's see if that works. Yeah, there we go. So that gives me, here's the excitation FFT, and here's the speech FFT with, oh, this is 8000 samples. Oh, because I only have 4000, I had a n of only 4000. All right. I want just the first 4000 hertz. Let's see, did that give me the first 4000 hertz? That gave me up to 2000 hertz. That's not right. Let me renormalize it by Fs over n. Let's see if that works. There we go. Now it's showing me the frequency in hertz from 0 to 4000. And here's the thing that I wanted to show you. You remember that the Fourier transform of the impulse train is an impulse train, right? The Fourier transform of the impulse train in the time domain is an impulse train in frequency where it has a 1, basically, every 100 hertz, 100, 200, 300, 400, 500. I told you then, that's only true for impulse trains. That's not true for speech. When you take the Fourier transform of the speech signal, it doesn't look like the time domain speech signal at all. Instead, what it looks like is this excitation FFT, but with some of the harmonics larger than others. And in particular, notice that this ah sound had a first formant at 700 hertz. And look at that, there's a big peak right at 700 hertz. That resonance at 700 hertz has created a big peak in the spectrum at 700 hertz. And there's another resonance at 1400 hertz. And look, there's that big peak in the spectrum right at 1400 hertz. And there's another peak at 2500 and another peak at 3500. So apparently when I create those time domain signals, let me plot those actually. So if I plot the speech signal, it looks like that. Oh, let me plot just the first 500 samples maybe. The speech signal in the time domain, it looks like this, right? In the time domain, we've got one sample every f0. I wonder if I can create a t-axis here. T is equal to np dot a range of length of speech, and the time should be, let's see, fs is the number of samples per second, and those are in samples, so I want to divide by fs because that will give me the time in seconds. And let me create an X label which says time in seconds. Let's see if that works. Time in seconds is, oh, because I need to give it the axis. All right, there we go. The time in seconds, every 10 milliseconds, right? Every 10 milliseconds, we get an impulse, the glottis closes, and that closing glottis excites the resonances of the vocal tract, right? Here's what the speech signal looks like in the time domain. It's a series of glottal closure events, and each of those glottal closure events excites those ringing in the vocal tract, that resonance of the vocal tract. And here's what it looks like in the frequency domain. We have all of the harmonics, which are the harmonics of the fundamental frequency, the harmonics of the pitch. So 100, 200, 300, 400, but the harmonic that has a resonant frequency attached to it, the resonances are 700, 1400, 2500. Each of those harmonics is higher in amplitude in the spectrum. So the Fourier transform of an impulse train is an impulse train, but the Fourier transform of speech is not speech. The Fourier transform of speech instead is another impulse train, but with higher amplitude at the frequencies where you had resonances in the time domain. The time domain had a resonance at 700 hertz, and so the spectrum has a peak at 700 hertz. The time domain had a resonance at 1400 hertz, and so the spectrum has a peak at 1400 hertz. And so in this way, the Fourier transform analysis gives us this wonderful information about exactly what vowel it was. We now have speech recognition. If you're playing a vowel and you want to know, is it ah or is it o? Well, we can look and see. The first formant is 700 and the second is 1400. So we can go back to our vowel chart and say, all right, 700 and 1400, that's an ah. If we had the first formant was 500 and the second one was 800, we would go back and say, oh, look, that's an O, right? Ah, that's an ah, oh, that's an O. We can go back and check from this Fourier transform, right? We can just look and see where are the peaks? What are the highest amplitudes? And once we've measured those, the frequency of each of those highest amplitudes, that tells us what vowel it is. So I've summarized that with the text here. The excitation FFT has peaks at every harmonic of F0. The speech FFT has all of those same peaks, but their amplitudes have now been scaled. So specifically, the harmonic at F1 has a high amplitude, the harmonic at F2 has a high amplitude, and so on. Those peaks are caused by the resonances. And notice also that if the bandwidth is smaller, the peak amplitude is higher. So the first formant has a bandwidth of 100. And so its peak amplitude is 600, is very high. The second harmonic has a bandwidth of 200. And so its peak amplitude is about half of the height of the first one, right? The third harmonic has a bandwidth of 300, and so its peak amplitude is about 1/3 of the height of the first one. We can check that. Let's check that by changing the amplitudes, the bandwidths of all of these resonances. Let's make them all 200 hertz all the way along. And if we change all of those bandwidths, we should get a different sound, but we should also get a spectrum where all of those peaks have about the same amplitude. Let's check and see if that works. Can I play it? Let me take this IPython. I'm curious to hear how that sounds. So let me add another window here where I listen to see how it sounds. Still sounds like actually. Changing all of the bandwidths didn't change the sound very much. Let's see what the spectrum looks like. Now, if I plot the spectrum, all of those formants are at roughly the same amplitude. Not exactly, but roughly. So the bandwidth controls the amplitude of the peak with some variation, but mostly the amplitude of the peak is 1 over the bandwidth, whereas the formant frequency controls the frequency at which that peak occurs. let's make it an O. Let's give it form at frequencies of 500 and 900. So let's see, let's make this 500 and we'll make this one 900. Now it's clearly an O sound. At least to me, that sounds very much like an O. And if I look at the speech FFT, look, there's the 500 and 900 are the frequencies of the first two formants. And the third and fourth formant are still at 2500 and 3500. So we have this very simple form now of automatic speech recognition. We can take the FFT and take the amplitude of the FFT and then look for the peaks in that amplitude. If the peaks are at 500 and 900, then we know that this vowel is O. If the peaks are at 700 and 1400, we know that the vowel is A. The more general formula is that we want to take the cosine and phase shift it by the phase of the Fourier transform component. So far, I've been throwing away the phase, right? If you go back here, you'll see that I took the absolute value of the FFT. I took the absolute value, I threw away the phase. The absolute value just ignores the phase and keeps only the absolute value. So here's the absolute value. I want to take the absolute value of the Fourier transform component, and I want to multiply that by the cosine at the frequency of that Fourier transform component, and add inside the cosine argument, I want to add the phase of that Fourier transform argument. So that's the general principle. I didn't need that because I'm just assuming 0 hertz, but I could add it in. Let me take the angle of the speech FFT at that harmonic. The harmonic is n over t naught, right? And I'll take the Lth harmonic. And I'll take L in the range from 1 to t naught over 2. I'll take the absolute value of the speech FFT at L times n over t naught, and I'll multiply that times the cosine of 2 pi ln over t naught. N is the time domain sequence of integers, right? The sample number. L is the harmonic number. And then t naught is the pitch period in samples. So I've got n over t naught gives me the time in fractions of one pitch period. And then I take 2 pi times L to tell me, L tells me which harmonic is it, the 0th, the first, the second, and so on. And I'm adding in the phase shift. The phase shift actually is not so interesting. It's not so important for the time. It's not at all important for the spectrum, but it is kind of important for the time domain signal. Let me go back to the awe that I started with so that I can show you the difference between a time domain signal that has the correct phase and one that has the incorrect phase. And let me create a figure here, which is 14 by 4. And let me create an axis. And I think I can just do ax plot and ax set mix label. Let's try that. All right, so here's my awe with incorrect phase. Let's play it back and make sure it's an awe. Okay, that sounds like awe. Sounds more like than ah. Well, anyway, that or ah sound. And let's plot its spectrum again. The spectrum completely ignored the phase, but let me try adding in the phase here. Let me try adding in the phase of that speech FFT, each of the harmonics, and see how that changes the way it looks in the time domain signal. There's a stem plot. Let me actually plot, rather than stem plot, let me just plot it. All right, so here's the first harmonic, the second, third, etc. And I get down to, oh, that's weird. That doesn't look accurate at all. This is not working the way it's supposed to. That's not what it should look like at all. That's strange. I think I have a bug in my code here somewhere. I'm sorry, there's some bug in this, but I'm not sure what it is. Speech FFT of L times N over T naught. N is the number of samples in the FFT. T naught is the number of samples per pitch period. So I have pitch periods per FFT multiplied by the number of the harmonic number There's a bug in this code and I'm not sure what it is. It looks like it's giving me a very strange plot here. Let's see what it sounds like. Yeah, that doesn't sound right at all. I'm getting the wrong harmonics here, and I think it has to do with this calculation. I think that's the wrong sample number from the FFT. Hmm. Yeah, well, I won't debug that now. I'll try to debug that before next week. There's for some reason this is giving me the wrong phase when I do it that way. But this, if we can get that formula correct, if we can get the right phase and the right amplitude, that will allow us to resynthesize the speech with the correct phase, which will make it sound a little bit more realistic. That'll just be taking the cosine of n times the correct frequency, added to the correct phase, and then multiplied by the correct amplitude in order to get the real speech signal. So here's the speech signal we get with just the correct amplitudes, and here's the speech signal that we get with the correct phases, if we could figure out how to fix that bug. Here I'm going to create these synthetic vowels, a, e, u, a, and o, create all 5 of them. And I've done that by setting the first formant frequency and the second formant frequency. And then for each of those plots, E, U, A, and O, I take the excitation and I pass it through a resonator with the correct F1, and then pass that through a resonator with the correct F2, and then pass that through a resonator with a formant of 2500, and pass that with a formant of 3500. And when I plot them, I get my synthetic A, E, U, A, and O. Let's play them back. Let me add a window after here and put in python.display.audio. Which speeches do I want to hear? Let's take speeches ah to start with. And let's play that back at a rate of fs and make sure that that sounds like an ah. All right, let's take speeches e and make sure that sounds like an e. Let's try the u and the a and the o. All right, so we have our 5 basic synthetic vowels, e, u, a, and o. We've added them all, added together all of the harmonics in order to create those vowels. Now let's plot the FFTs of all of those. I'm going to plot the FFT. I've got the wrong length signal again here. Let's see. F should be equal to np dot a range length of the speech signal. Over fs, times fs is in samples per second, so times fs over the length of the FFT. Let's see if that works. There we go. Okay, I've got no, it's showing the full 8,000 there, isn't it? All right, so here's the here's the synthetic ah between 0 and 4,000 hertz. It has peaks at 700 and at 1,400 and at 2,500 and at 3,500. Here's the synthetic E. Let's see, the E should have peaks at 350 and at 2,300 hertz. So let's see. It looks like it has a peak at 350 and another peak at 2,300, and then again at 2,500, and then again at 3,500. The synthetic U should have peaks at 400 and 800. Let's see, when I plot the spectrum of the synthetic U, it has a peak at 400 and one at 800. The synthetic A has peaks at 500 and at 2,100, and then again at 2,500 and 3,500. The synthetic O has a peak at 500 and then another peak at 900. And then its next peak is all the way over here at 2,500, and then this last peak is over here at 3,500. Oh, here's a display again, so I can play each of those back in order to see how it sounds. There's the A and the O and so on. And so you can see that we can actually do automatic speech recognition by just looking at the spectrum and finding where are its peaks. That allows us to tell what vowel it was. So far, we've just done, all that we've done is synthesis, but we could do recognition by creating some kind of pattern matching algorithm that would look at this spectrum and just pick out the peaks. And those peaks would tell us the formant frequencies. Instead, now though, I'm going to try to use the Fourier synthesis equation to resynthesize speech. Oh, and now I have even a bug in the formula. Let's see what the code says. The help file in the code says we want to resynthesize the speech by taking the number of harmonics and the input Fourier transform and the pitch period. And then we want to recreate the sum from L equals 1 to the number of harmonics, the amplitude of the Fourier transform at L times n over T naught, multiplied by the cosine at that frequency, 2 pi L times n over T naught, plus the angle at L times capital N over T naught. So let's try just creating that code and see if that can give us the spectrum of the ah. Let me go to homework9.py. And let me cancel out this runtime error. And now what I want to do is I want to create a signal which has, what is its length? Its length will be the length of the Fourier transform. So let's say capital N is equal to the length of capital X. And then small x will be just zeros of a length of capital N. And then I want to, for L in the range from 1 to number of harmonics. So I want it to go from 1 to number of harmonics. So I'll take 1 up to number of harmonics plus 1, right? Because the range function only returns integers up to 1 minus its top, up to its top argument minus 1. So I'll just do up to its top argument minus 1. And let me say that x is equal to, n is equal to a range up to capital N. So x will be equal to 2 over capital N times I'm going to take the previous value of x and then I'm going to add in the next harmonic. I'm taking the sum over these harmonics here. And I want to add in, first of all, the absolute value of the Fourier transform at L times capital N over T naught. And I want to multiply that by the cosine of 2 times pi times L times N over T naught plus the angle of the Fourier transform at L times N over T naught. All right. Oh, I want to close the cosine. So I'm creating an x, which is just accumulating each of these harmonics at this absolute value and at this angle. And that should give us back again a speech signal, which this might still have the same bug in it that I described before, but at least it should sound approximately like the correct vowel. Let's try loading it and plotting it. Oh, I need to return x. I need to return the time domain signal. So let me add in each of those harmonics. And after I've added in each of those harmonics, I'll return the time domain signal. And that should give me back again then a copy of the vowel that I can play. So there's my ah. I've added together all those samples. I get something that looks approximately ah-like and should sound approximately ah-like. There we go. Good. So once you've done that, you can, if you want, you can check right in the notebook to make sure that it matches. Oh, well, I don't have, I'm not, the grading is not working here, but that's okay. We're not going to auto grade anyway. So instead, let's open up GitHub Desktop and check it in. Here's GitHub Desktop, and let me go ahead and say homework 9. I've done homework 9. And we'll go ahead and commit this to my local repository and then push it to origin. And once you've committed that and pushed it, then you should be able to go to your own GitHub account and go to your own copy of Intro Speech Understanding, 2025 Spring, Lecture 9, Homework 9, and you should be able to see all of the things that you just wrote. So copy this URL and go to the course. Let's see, let me open up the course. And if you go to homework 9, then you should see something that says enter the URL for your copy of homework9.py, and you should be able to enter the URL here, and then I'll check it manually and grade those. That's all for this week. So let's go ahead and do the do attendance. Okay, here, please go ahead and register your attendance with this code. I think there are 10 of you here, so we should get 9 people signed up. Free already, great. Can we get 6 more people to register attendance? Up to 5 people now. Do we have 4 more? Oh, there's 7 people. Do we have 2 more people? All right. Thanks, everyone. I'll see you all next week then. Have a good week.